Welcome to DWBIADDA channel. Please subscribe for latest training videos.
Hello, welcome to the Pytorch tutorial. This is the third video of the Pytorch tutorial series. In the last video, we discussed about Pytorch datasets and data loader. Before we move on to creating actual neural networks in Pytorch, we need to understand one more concept that is called Autograd. Autograd is necessary for backpropagation, and Pytorch, by using Autograd, makes backpropagation really easy. So let's first understand what is a backpropagation and what is a forward propagation in a neural network. Let's say we have this simple neural network where I have only one neuron and I have only one input data, that is X, and X has a weight of W and a bias of form B. So in this neuron, I have our data in the form Z equals to W multiplied by X plus B. So it's a straight linear equation. So what happens after that? We pass it through an excitation state where we fit the value of Z through sigmoid function and we get our Y hat, that is our predicted value for Y. So this is what happens in a forward pass. All this computation, as you can see, it looks like a graph. In the first video, I talked about computation graph. This is how a computation graph looks like. After we have computed Y hat, we need to calculate loss. Now, loss function can be of any form. Here I'm taking mean squared error, which is basically mean of actual Y minus predicted Y, its square. Here I haven't shown the mean, it's just the square of the difference, since I only have one value, so it doesn't matter. But in the real scenario, you have to take a mean of all the samples you have. So once I have the loss function, we are ready to calculate the backpropagation stage of the neural network. So this is what happens in a backpropagation stage. We calculate the gradient of each step. First, we calculate the partial differentiation of L with respect to our Y hat, and then we calculate partial differentiation of Y hat with respect to Z, and then partial differentiation of Z with respect to W. But why are we exactly doing that? Actually, we need the partial differentiation of loss with respect to W so that we can update it in the next stage with our learning rate. By the chain rule of partial differentiation, we can show that delta L divided by delta W is equal to delta L divided by delta Y hat multiplied by delta Y hat by delta Z multiplied by delta Z by delta W. In the same way, we calculate the partial differentiation with respect to B, where we take all the three partial differentiations with respect to Y hat, with respect to Z, and with respect to B, and finally we calculate the partial differentiation of loss with respect to B. So what are we doing with these terms? Delta L by delta W and delta L by delta B. This is the heart of backpropagation stage. We want to update our weights and our biases with respect to the differentiation, and we do that using alpha, which is the learning rate. So the formula is W equals to W minus alpha multiplied by delta L by delta W, and B equals to B minus alpha multiplied by delta L by delta B. let's look into our code. Pytorch makes it really easy so that you don't have to do all this calculation. It does it for you. Hence, Pytorch is so popular. I talked about it in the first lecture where I explained how Pytorch creates a dynamic computation graph apart from the other machine learning platform which creates static computation graph. So Pytorch is much better in that way. So first we import torch and we create one variable that has a float 30. We call it x. We store a float 40 in W and we store a float value of 50 in B. Notice one thing, that we don't need gradients with respect to x. So in this case, requires grad flag is set to false, which is its default, so we didn't mention it. But in case of W and B, we have set the flag requires grad equals to true because we need gradients with respect to W and B. Just to check whether it's the leaf node, we are creating this code b.isLeaf. If you check it with W and X, we'll find that everything is true here. The reason is, in this case, this is the first stage of our calculation, z equals to W into X plus B. So all of these are leaf node. And in this case, we are not going to go further and put z through sigmoid function. Otherwise, z would become a leaf as well. In this case, we are going to keep things simple and we're going to show that how Autograd calculates the partial differentiations. So we just need to understand the concept of Autograd. So what we are doing is we are calculating z as z equals to wx plus b. So if you have a very little understanding of mathematics, you will find that delta z by delta w will become x and delta z delta b will become 1, and in this case the value of x is 30, so delta z by delta w will become 30 and delta z by delta b will remain 1. So let's calculate z. Obviously z is a tensor of value 1250 and it's a float value. 30 multiplied by 40 is 1200 and plus 50 is 1250. So math checks out. Very good. If you want to check whether z is a leaf, just you have to write the dot is leaf and you will see it's false since w, x and b are leaves and z is the computation based on all these three variables. So this is not a lift, this is the parent now, and w, x and b are leaves. But if we calculate some y hat and sigmoid z, z will become a leaf. Anyway, let's calculate the gradient. To calculate the gradient in Pytorch, all you have to do is write z dot backward. That's it. It does all the backward calculations for you. When you call backward function, it calls torch dot autograd dot backward function, which calculates the backward computation. It also creates the graph, the computation graph for the differentiation. So let's check the value of delta z by delta w. All you have to do is write w dot grad. Remember, we stored 40 in w, and after backward calculation, the value of delta z with respect to w will be stored in w dot grad. As expected, the value is 30. and if you check the value of delta z by delta b, the value is stored in b.grad, and once we call this one, we see tensor 1, which is as expected. So PyTorch makes backpropagation really easy so that you don't have to calculate all the differentiation and write the functions manually. It's all calculated and it stores the values properly in grad. Thanks for watching.